Mr. Joshi has been a valued member of Laser Technology Group at BLM Group for over 20 years, bringing with him over 3 decades of expertise in industrial laser applications such as cutting and welding. His extensive experience encompasses various aspects including system design, operation, project management, application development, and system innovation, with particular focus on CO2 laser generators and fiber lasers. Today, Mr. Joshi will share his insights on trends and challenges in tube bending. So please welcome Mr. Joshi.
Thanks for the introduction. Basically, I'm an R&D person, so lasers was my background, but last few years I've been following Indian market as market development assistant, let us say. And today I'm going to speak, since the subject was challenges in tube metal forming, I'm going to say a few things about tube bending, which is one of the core competencies of our group. So I will share my presentation and trends and challenges in tube bending. Uh, uh, some of the delegates who are participating in this webinar may look at this picture and think that this is a bad part. But I would like to tell them that this is a good part, and how it is good part I will explain at the end of the presentation. Uh, Thanks OEM Update for giving me this opportunity to share a few things that I know about tube bending and metal forming. And thanks to all the panelists who have presented before me. I learned a few things from them. I didn't know a lot of things what they were talking about, so it was a good learning opportunity for me. So let's go to the next slide. Just a quick introduction to BLM Group. We are an Italian group. We have been manufacturing tube processing machines for the last 60 years. Our product lines are mentioned here. We manufacture tube bending machines, wire bending machines, tube and forming machines, laser tube cutting machines, sheet and tube laser cutting machines. And we develop all the software that is used on our machines and offline programming systems in-house. So what all was said about first time right, just in time, preventive maintenance and automation and integration with ERP and calendarization, scheduling, all these things. All our softwares do all those things for all our manufacturing machines. And we are more than 60-year-old group, and all our manufacturing is in Italy. It is divided into 3 main campuses. We are about 900 people totally, and about 480 million euro turnover. So we are not very big company, but not a small company as well. Now let's come to trends in tube bending. As you know, everything is getting smaller. Everything is getting compact. Be it an automotive, be it your coffee machine, be it your microwave, be it refrigerator. So the compactness is the key word. And since these things are getting compact, all the components also have to follow the suit. And naturally, the tubular components, which are in all these subsystems, like in automotive or furniture, or they are also getting smaller and smaller. So when you have smaller tubular component, it means that the bending radiuses are very tight. Earlier, when there was space, you can have large bending radius and component would sit there comfortably. But now with these things, the bending radius means with here, if you can see my cursor, this radius, earlier it could have been a very large radius, but now it is a very short radius because it has to be very compact. So bending processes have to adopt to these trends and develop new techniques to bend tubes. So let's see which are the different methods of tube bending which are normally used in the field. Rotary draw bending is the first method. Then next is compression bending. Third is roll bending, and fourth is stretch forming. So BLM Group manufactures machines which cover the first 3 methods. And the fourth method, we do not manufacture any machines for stretch forming. But today we'll be focusing our presentation on only on rotary draw bending because that is the process which is mainly used for tight bends. So what are the parameters that govern the bending process? Or how do you decide whether a given bend is feasible or not feasible, whether it's an easy bend or difficult bend? So these are basically two parameters which are used generally in the uh, industry. One is outside diameter divided by wall thickness. So you can understand that as the outside diameter becomes bigger and bigger, it is more and more difficult to have uh, sharp bends, and as well as the wall thickness is it becomes thinner and thinner. There is limitation to how much you can stretch the material, and then it is more and more difficult to obtain a nice quality bend because if the raw material is too thin, what happens is that during bending process, it will just tear off by stretching. Because when you are bending the tube in this area, if you can see my cursor, the material is being stretched and inside it is being compressed. So here thinning takes place and here thickening takes place. So there is a wall thickness difference on the two sides of the bend. So if the material is too thin, then here in this area on the outside, which is called extrados, it will break. So this is one parameter which is considered while judging the feasibility of bending a tube. The next is CLR divided by OD. So CLR is the mean bending radius, center line radius, and the smaller it is, difficult it is to bend because you are bending the tube with a very sharp radius and the stretching on the outside, stretching in the outside is much more compared to the center line. So the smaller the center line radius, more difficult it is. So you might have heard 1D bends or 2D bends or 3D bends, this kind of terminology. 1D bend means CLR is equal to outside diameter of the tube. 2D bend is CLR is two times the outside diameter of the tube. Normally, any CLR which is smaller than 2.5 is considered to be a bend where you need to take some precaution in getting for getting good quality bends. Now this CLR divided by OD, if you invert it, it is OD divided by CLR, and that is used to get this equation, which is called difficulty ratio, where this and this is multiplied to get a number which bigger the number, more difficult it is to uh, get that uh, feasibility easily. So larger the outside diameter, more difficult it is, smaller the wall thickness, more difficult, smaller the CLR, more difficult. And another important parameter is also bend angle, because if the bend angle is a very shallow angle, let's say 10 degrees, then the difference between the extrados and intrados is very little. So the tube doesn't suffer a lot and the bend is easy. But if this bend angle is 180 degrees, the difficulty of bend goes up drastically. Another parameter which is important is also material properties, because if the material is ductile, which has good elongation, then it is easy to bend the tube. But if the material is hard, material is not ductile, it is brittle, then you will break the tube while bending. So these are some of the numbers that I am just mentioning because it depends a lot. This elongation depends a lot on the material composition, how it has been annealed, and a lot of other things. For example, in case of aluminum, we have seen that if aluminum, if it is fresh, you can bend it easily and you can get very good bends. But if it is lying outside, getting oxidized, and it is becoming harder, then it will just the same material after 1 month. If you try to bend it, it will break. So it depends upon material qualities also, material properties also. Now, I am not a material scientist, so I won't go into details of these, but I think people who are uh, experts in materials would understand what I'm trying to say. Now, here are some examples. And you will see that this DR, the difficulty ratio that we are talking about, this is considered to be benchmark, which is a very DR8 is a generally simple band. You don't have to do much about it. Now, there are various citations in the literature which say that DR equal to 30 is difficult band. Somebody says DR equal to 40 is a difficult band. Somebody says DR is equal to 20 is a difficult band. It depends on various factors that we have mentioned earlier. But we have been working to get these difficult bends, and we are focusing on how to increase this DR number. And lately, we have been able to bend DR. I think this is hidden by this panel 767. So here we were bending a tube of 110 millimeter dia. It's a stainless steel tube with 2 millimeter wall thickness, and CLR was 90 millimeters. So this was a difficult bend. We had to do really some special things to get this good quality bend. And this was meant for a furniture item, which we will see in the next uh, slide. So this was a bar stool kind of thing, which is designer designed it, and he wanted to bend these tubes with this tight radius, and this is the part which is bent on our machines. And now we'll see the video. I hope it starts. Yes. Can you see the video? I hope so.
Yes, sir.
Okay. So here you will see this bar stool concept, which has bend tubes, the big bend tube, and as well as some smaller bend tubes to support the seat. And all these parts were manufactured on our machines, on our sheet cutting machines. The sheet part was cut, and this tubular part was bent on our machine. Now, here you will see this. If you see carefully, there is a mandrel movement inside the tube. When you will see the tube is supported by a mandrel which is inside, and there is lubrication. So that is another factor. You would have seen something moving backwards. That was the mandrel movement, and this tube was bent, and afterwards it was cut using a 3D laser cutting machine that we manufacture, and you can see it here. To generate these slots and the end cuts, etc. And finally, that stool was assembled and welded and was ready. So this requirement of very tight bends is coming from aerospace and automotive, but it is coming also from this field of furniture design. As you know, Milan area, we are close to Milan. Our headquarters is close to Milan, where I'm sitting now. This area is well known for furniture design, and we have a lot of furniture designers in this area. They throw us challenges, and we try to accept those challenges and find solutions. And this was one of them. As I mentioned earlier, we have more than 60 years experience in tube bending machines, and this experience has been transformed into user-friendly machines. All our machines are all electric machines, so every movement on the machine is controlled by a CNC axis. So we have complete control of the bending process, because we can not only control the position of an axis, but the force that it exerts on the tube is also precisely controlled. Then to get this good quality bends, we had to develop some fine motion control algorithms. So how the various axes simultaneously move to get the best result. So all those things are developed in-house. And last but not the least, the bending tool design is also plays a very important role in getting good quality bends. Because if that, I always say that a bending machine is like a piano and the tool is like a player. I mean, if you don't have a good tool, then your good bending machine is not useful. And if you have a good tool, but you don't have a good bending machine, then even then you won't get the good results. So you require good matching of both these uh, things. I mean, good machine and good tool. I think I have finished. Thanks for your attention. This is my email address. Please feel free to contact me if you have any questions or if you have any requirements in the tube processing.
Mr. Joshi, for briefing us about trends and challenges in tube bending.